Hello, dears. Welcome to the Science for Sleep channel. In the vast and silent emptiness of the constellation Leo, some 120 light years away from our home planet, a discovery quietly emerged that may invite humanity to gently reconsider its place in the universe. It does not announce itself with loud explosions, dazzling lights, or dramatic flashes that demand attention. Instead, it whispers softly, hidden within subtle streams of data, calm numerical patterns, and the patient, unblinking gaze of an unwavering telescope scanning the cosmos night after night, capturing light that has traveled across unimaginable distances, untouched by human eyes for over a century. The James Webb Space Telescope, humanity's sharpest and most attentive eye, turned toward the heavens, has observed a planet bathed in the gentle warmth of its star, lying precisely within the narrow range of temperatures that make life possible. Yet what makes this discovery extraordinary is not simply its warmth or its carefully tuned orbit. It is the presence of an atmosphere that carries chemical traces uniquely connected to living systems, a delicate, almost intimate signature of life, written in molecules and light, faint but persistent, waiting patiently for us to perceive it. These traces are not vague hints or fleeting suggestions. They are precise molecular fingerprints, intricate and deliberate, the kind that scientists have dreamed of for decades, hoping to glimpse beyond the boundaries of our solar system. Each line of the spectrum, each tiny absorption in the starlight, tells a story of chemistry that could have no origin except life itself. It is a quiet narrative unfolding across the void, whispering of processes that only living systems can orchestrate, of cycles of energy and transformation that shape and sustain life in ways both subtle and profound. It is the planet speaking in a language of molecules and photons, offering the first signs of a story that began billions of years ago, unfolding silently in the distant reaches of space. The researchers studying this data are 99.7% confident in its significance. In the language of science, this is almost absolute certainty, a figure that leaves little room for coincidence, instrumental error, or random chance. This is a clear, persistent signal from across the stars, a cosmic message that has traveled for more than a century to reach our instruments, bearing the story of a world that is alive in ways we are only beginning to understand. It is a message written not in words or images, but in the delicate chemistry of an alien sky. In some ways, this world may even surpass Earth in its potential to support life. This realization alone challenges centuries of assumptions about what makes a planet truly habitable. For it is not only the presence of water or the right temperature that matters, but the entire orchestration of atmosphere, chemistry, and energy working in concert to create a living, breathing planetary system, a symphony of conditions that allows life not just to exist, but to flourish. If you enjoy calm, reflective journeys into the universe, into life itself, and into the quiet mysteries of existence, now is a good moment to take a deep breath, let your mind drift among the stars, and gently settle into this cosmic story. Your curiosity is a bridge across space, connecting us to the faint whispers of distant worlds, to the subtle messages embedded in light that has traveled for over 100 years, and to the first tentative signs of life beyond our own. Close your eyes if you wish, and let your imagination float far from Earth, among alien skies and oceans of possibilities. Picture a planet orbiting a dim, red sun, its surface bathed in steady warmth, its oceans flowing beneath skies tinged with the light of a star you will never touch, yet whose glow has traversed light years to meet your gaze. Imagine a world where time feels different, where evolution unfolds in a rhythm set by a patient star, and life, whatever form it may take, moves quietly beneath clouds, across oceans, and through the air. This is where our journey begins. On the morning of December 1st, the James Webb Space Telescope, humanity's most precise instrument for peering into the cosmos, transmitted terabytes of infrared data back to Earth. Each packet of information carried measurements of unparalleled detail, far beyond what any observatory had ever achieved, capturing nuances of light that tell stories billions of years in the making, stories written in the delicate fingerprints of chemistry, preserved across space and time. Hidden within this immense stream of data was a faint beam of starlight, traveling across the cold, silent void of space for 120 years. It had left its star long before many of us were born, carrying with it the subtle story of a distant, alien world, a world whose existence we could only imagine until now, a world whispering its secrets across the abyss. At the University of Cambridge, astronomer Niku Madhusudan meticulously examined the wavelengths of this ancient starlight. Line by line, graph by graph, he traced the ways in which the light had been altered as it passed through the atmosphere of this remote planet. Every dip, every absorption feature was a clue, a whisper of processes invisible to the eye, but inscribed in the language of chemistry, a language that speaks of life itself. What he saw was quietly extraordinary. It did not merely suggest something unusual. It revealed a chemical signature that could not arise from any known non-living process: dimethyl sulfide. On Earth, this molecule is not produced by geology or chemistry alone. Its presence is intimately tied to life itself, a subtle yet definitive imprint of biological activity, a molecular fingerprint that signals the presence of living systems shaping their environment. Dimethyl sulfide emerges solely through the actions of living organisms. It is a persistent, delicate byproduct of complex biological cycles, dependent on energy transformations and enzymatic processes that only life can generate. The discovery of this molecule on K218b is in essence a message from a living world, an echo of alien biology, carrying the fingerprints of life across the gulf of interstellar space, a whisper that has traversed time, light years, and the vacuum between stars to reach us. It is a quiet, profound moment, the first tangible hint that life does not belong solely to Earth, that the universe may be filled with worlds alive in ways both familiar and utterly alien, waiting for us to listen, to understand, and to wonder. And this was no faint or ambiguous signal. It was strong, clear, and undeniable, a gentle but insistent whisper from across the cosmos, traveling over 120 light years through empty space, patiently waiting to be heard. The probability that this detection was a random fluke or an instrumental error is less than 0.3%. In other words, the odds that we are wrong are astronomically low, so low that the signal practically insists on being recognized for what it is, the first tangible hint of life beyond our solar system. In this quiet, contemplative moment, the James Webb Space Telescope may have achieved what generations of astronomers have long dreamed of. For decades, scientists have sought a reliable, indisputable sign, a chemical fingerprint, a whisper from another world that confirms we are not alone. And now, at long last, it may have arrived. The planet bearing this extraordinary signature is called K218b. It orbits a small, red dwarf star, moving gracefully within the habitable zone, the narrow celestial ring where liquid water can persist on a planet's surface. Its orbit is steady, unhurried, almost meditative, as if the planet itself has been given time to cultivate life across eons. Yet K218b is unlike any world we have ever known. It is not a twin of Earth. It is a super-Earth with a mass roughly 8.6 times that of our planet. For years, astronomers assumed planets of this size and composition were unlikely to harbor life, imagining their thick hydrogen atmospheres as smothering blankets that would crush oceans or destabilize solid surfaces. K218b defies these assumptions spectacularly. Its thick, hydrogen-rich atmosphere, rather than being hostile, stabilizes the planet. It creates a gentle, balanced greenhouse effect, retaining heat and distributing it evenly across the globe, smoothing out temperature extremes that might otherwise render the planet inhospitable. This mechanism allows vast oceans to remain liquid, flowing quietly and continuously across the surface, forming a stable environment for biological activity. Water, the essential solvent for life, is likely abundant, calm, and persistent, nurturing life as it unfolds in subtle, planetary-scale rhythms. Every observation we make about K218b reminds us that life is more than simple habitability. It is the delicate balance of chemistry, energy, and environment, a planetary symphony orchestrated over billions of years. In the spectrum of a distant star, in the faint whispers of light filtered through alien skies, we glimpse this symphony. It is a reminder that life is not merely possible here, it may be thriving, quietly persistent, and profoundly interconnected with the planet itself. Measurements suggest a surface temperature of roughly 49 degrees Celsius. While this may feel warm by human standards, it is comfortably within the tolerance of many forms of life. It may even create a stable, nurturing environment for the emergence and flourishing of complex ecosystems. The temperature on K218b is neither so high that oceans would boil away into the vacuum of space, nor so low that water would freeze into endless sheets of unyielding ice. Instead, it rests within a narrow and precious window, a delicate balance where molecular chemistry and the rhythms of biology can coexist, intertwine, and interact continuously. Here, life may have the time, the space, and the stability to grow quietly, steadily, and profoundly, flourishing in ways both subtle and planetary in scale. For many months, Madhusudan and his research team observed this distant world with unwavering patience. They traced K218b's slow, graceful passage across the face of its gentle red dwarf star, noting each subtle variation in the starlight. Each of these transits, was a small cosmic invitation, allowing a fraction of starlight to filter through the planet's atmosphere. This light, altered in minute but telling ways, carried encoded whispers of gases it had brushed against traces of chemistry, forged over billions of years of planetary and perhaps biological activity. Through painstaking, line-by-line analysis, water vapor was detected first. This familiar molecule, so central to life as we know it, appeared as a beacon of possibility. Its presence hinted at active atmospheric dynamics, and perhaps even global oceans stretching across the planet's surface. Water alone suggested that the planet could sustain life, or, at the very least, provide the conditions necessary for living processes to take root and evolve over geological timescales. Then came methane, a molecule that evokes both curiosity and caution, followed by carbon dioxide, the silent regulator of planetary climate. Together, these molecules painted a tentative picture promising, yet still open to natural explanations. Methane and carbon dioxide can arise from volcanic eruptions, chemical reactions in rocks, or radiation from the host star. They were intriguing hints, yet alone they could not confirm life. And then, almost imperceptibly, quietly, came dimethyl sulfide. This single molecule transformed the entire understanding of the planet. Its presence elevated a hopeful observation into a potentially historic revelation. Dimethyl sulfide is so intimately tied to living processes that its detection in an alien atmosphere is almost like reading a glowing, microscopic signature left by life itself across the interstellar void. On Earth, dimethyl sulfide is primarily produced by phytoplankton, the tiny but powerful organisms that drive the chemistry of our oceans, generating vast effects on climate and biology alike. It is also produced by certain bacteria and algae through intricate metabolic pathways, delicate, purposeful chemical cycles that reflect the active work of living systems. No volcanic eruption, no tectonic upheaval, no purely chemical reaction has ever been observed to generate dimethyl sulfide in the concentrations detected on K218b. Its origin is almost certainly biological, a product of life actively shaping its planetary environment. For this reason, scientists regard dimethyl sulfide as one of the most decisive biosignatures known. It is far more telling than oxygen, which can accumulate through photodissociation of water, or methane, which can emerge from deep geological processes. Dimethyl sulfide, however, almost exclusively signals the presence of ongoing biology-active processes that shape and sustain life in real time, rather than leaving behind only fossil remnants from a distant, ancient era. Statistical analysis confirms the remarkable significance of this finding. The chance that this detection is false is less than 0.3%. In scientific terms, this corresponds to a 3 sigma confidence level, a degree of reliability that is rare, compelling, and difficult to ignore. Even with careful caution and a desire for further verification, the evidence compels scientists to consider seriously that life may exist far beyond Earth, in a place where we once could only imagine its possibility. If future observations validate this discovery, humanity may be standing at the threshold of one of its most profound realizations. The age-old question, are we alone in the universe? Could shift from philosophical speculation to observable science. from wonder to knowledge, from hope to evidence. K218b is no ordinary planet. It belongs to the class of super-Earths, worlds larger than our home, yet smaller than Neptune, occupying a middle ground in planetary diversity. For decades, astronomers assumed such worlds were inhospitable, cloaked in thick gaseous envelopes, lacking stable surfaces, and unsuitable for the intricate processes of life. K218b defies these assumptions with elegance and subtlety. This planet may be a prime example of what scientists now call a Hycean world, a world enveloped in a thick, hydrogen-rich atmosphere, beneath which lie global oceans. In these oceans, combined with gentle, planet-wide atmospheric circulation, conditions may remain remarkably stable across the entire surface. Life, if present, could thrive in these oceans, sheltered and nourished by the balance between heat, pressure, and chemistry. Its strong gravity allows K218b to retain its atmosphere and oceans over billions of years, unlike Earth, which gradually loses small amounts of gases to space. This retention is critical for sustaining a long-term, habitable environment, providing the stability that evolutionary processes need to develop complexity and resilience. The thick hydrogen atmosphere also distributes heat evenly across the globe. Even if K218b is tidally locked, its day side basking in constant starlight, its night side in perpetual shadow, the circulation of gases ensures neither hemisphere becomes extreme. Nearly the entire surface could sustain liquid water, offering a continuous, life-friendly environment where chemical and biological processes can persist without interruption. In every observation, K218b challenges our preconceptions about what makes a world habitable. It reminds us that life is not simply about Earth-like conditions, but about a planetary balance, an intricate interplay of atmosphere, ocean, and chemistry, unfolding over time, scales that are immense to human perception. Here, across the gulf of space, we may be glimpsing the subtle rhythms of life as it unfolds on a distant stage, reminding us that the universe is not empty, but quietly, profoundly alive. Another remarkable detail is the near absence of ammonia in K218b's atmosphere. This subtle observation may indicate that biological processes are actively consuming it, quietly reshaping the chemical balance of the planet on a global scale. Life here may not merely exist as isolated pockets. It may be engineering its world, modulating atmospheric composition, oceans, and chemistry in a sophisticated planetary symphony. The very fabric of the atmosphere hints at a living system, continuously interacting with its environment, leaving traces of its activity for distant observers to detect. Taken together, these features make the K218 system appear almost delicately tuned for life, a protective atmosphere that shields and stabilizes, oceans that could stretch unbroken across vast expanses, a stable orbit that avoids catastrophic extremes, and a patient, long-lived star offering seemingly endless time for evolution to unfold. Each element contributes to a harmonious balance, suggesting a world where biology and planetary physics co-evolve in intricate synchrony. K218b is transforming the way humanity envisions life beyond Earth. We no longer need to search only for worlds that mirror our own familiar environment. Life may arise under chemistries very different from ours, beneath hydrogen-rich skies, on planets far larger than our home, under conditions that challenge our imagination. Perhaps the life we have been seeking is not a mirror of ourselves at all. Perhaps it is strange, unfamiliar, wondrous, a distant cousin of life rather than a twin. Perhaps, then, the life on K218b is alien yet familiar in essence, different in scale, in chemical pathways, in evolutionary history, yet sharing the fundamental principles of biology, the drive to grow, to adapt, to persist, to harness energy, and to reshape the world around it. It may utilize chemical strategies we have never observed, yet its existence would affirm that life is resilient, versatile, and inevitable wherever conditions permit. If life can emerge and flourish on a super-Earth wrapped in a thick, hydrogen-rich atmosphere, then our prior estimates of the number of potentially habitable worlds in the Milky Way are almost certainly too low. The universe may be teeming with life, not rare islands in an empty sea, but countless planets quietly hosting chemistry, biology, and ecosystems, each unique, yet bound by shared cosmic principles. The galaxy may not be sparsely populated with possibilities, but densely alive, awaiting our first careful observations. Red dwarf stars, once considered minor actors in the search for life, now claim the central stage. These unassuming stars, small, dim, and often overlooked, may host the majority of habitable worlds, quietly nurturing them for billions, perhaps even trillions of years. In this cosmic story, they are not supporting characters, but the steady heartbeat of life's potential, providing the constancy and patience that planetary evolution requires. The discovery of K218b is therefore far more than the identification of another exoplanet. It is the unveiling of an immense ocean of possibilities, a landscape of potential stretching across light years, suggesting that the universe may be far more alive, far more intricate, and far more dynamic than our imagination has yet allowed. It challenges us to expand our definitions of life, habitability, and planetary stewardship. Yet a planet cannot be fully understood in isolation from its star. Stars are not mere sources of light or warmth. They are cosmic timekeepers, shaping climates, orchestrating atmospheric chemistry, and determining the long-term evolutionary potential of the worlds they host. K218b's greatest gift may not lie solely in its oceans, its atmosphere, or its hydrogen-rich envelope, but in its star itself, K2-18. K2-18 is a red dwarf, small, cool, and dim compared to our Sunday. Yet beneath this modest appearance lies extraordinary potential. Because it burns its fuel slowly and steadily, it offers life almost limitless time to evolve, to experiment with biological strategies, and to grow in ways our own Earth could scarcely match. Unlike the Sun, whose lifespan is roughly 10 billion years, and whose future includes a red giant phase that could sterilize Earth, K2-18 may shine for trillions of years. For life on K2-18b, this is a luxury beyond comprehension. On Earth, simple microorganisms required nearly 4 billion years to give rise to complex ecosystems, nearly half the Sun's lifetime. On K2-18b, life may have uninterrupted time stretching across unimaginable epochs, evolving forms and strategies that surpass our current understanding. A star that shines with such long-term constancy offers more than light. It provides stability, patience, and continuity, the essential scaffolding for life to innovate, adapt, and thrive. Ecosystems may evolve entirely new principles, leveraging chemistry in ways that are alien yet internally coherent. Biological complexity could unfold gradually and safely, nurtured by the star's unwavering energy. Red dwarfs also offer remarkable predictability. Unlike the Sun, whose luminosity gradually changes over time, subtly altering climates and occasionally destabilizing environments, K20-18 shines with remarkable steadiness, delivering energy reliably across billions of years. This stability is crucial for the long-term maintenance of life, allowing evolution to explore the full range of possibilities without catastrophic interruptions. Of course, red dwarfs carry their own risks. In youth, many flare violently, releasing bursts of radiation that can sterilize nearby planets. Yet K2-18 appears serene, a well-behaved red dwarf, providing a calm environment where life could persist and flourish for eons. Its stability is a quiet gift, a cosmic lullaby that allows ecosystems to breathe, grow, and adapt without the threat of sudden annihilation. Taken together, these factors create a remarkable and almost poetic picture. K2-18b is a planet shielded by a thick, stabilizing atmosphere, immersed in global oceans, orbiting steadily within the habitable zone of a patient, long-lived star. And it is only through the extraordinary vision of the James Webb Space Telescope that we have been able to detect this distant whisper of life carried across 120 light-years. This discovery reminds us that the universe is not an empty void, but a living, breathing system, rich with chemical, geological, and potentially biological complexity. K2-18b offers a glimpse into what may be common across the galaxy. Planets where life quietly engineers its world, patiently evolves over unimaginable timescales, and leaves traces for distant civilizations to discover. The universe, it seems, is whispering back to us, and at last, we are beginning to listen. James Webb is not simply a telescope. It is a finely tuned instrument, the culmination of decades of ingenuity, collaboration, and engineering, designed with extraordinary precision to reveal the faintest, most elusive secrets of the cosmos. It can detect chemical signatures so subtle that, without it, they would remain hidden in the vast, indifferent silence of space, allowing humanity to reach across 120 light-years and glimpse the molecular fingerprint of a distant world, a whisper of life encoded in the starlight. Its power does not lie solely in its enormous golden mirror, though that is itself a marvel of engineering, an achievement of human craftsmanship and imagination. The telescope's location, 1.5 million kilometers from Earth at Lagrange Point 2, is equally crucial. Here, where the gravitational pulls of Earth, Moon, and Sun delicately balance, Webb floats in perfect stability. Shielded from the heat, light, and interference of nearby celestial bodies, it can observe the cosmos with an almost meditative calm, as if listening in a quiet cathedral of stars. Within this serene, almost sacred shadow, the telescope's instruments are cooled to temperatures just a few degrees above absolute zero, colder than the vast majority of the universe itself. Infrared light, after all, is the language of heat. If Webb were warm, it would drown out the delicate signals from K218b entirely, silencing the whispers of molecules that have traveled across the void for more than a century. By remaining cold, the telescope isolates these faint molecular fingerprints, separating them from the cosmic noise and from its own machinery, and allows humanity to hear the subtle song of a distant atmosphere. The telescope's 18 hexagonal mirror segments, coated in gold, work together in near-perfect harmony, aligned with precision, measured in fractions of a millimeter less than the width of a human hair. This golden geometry is not mere ornamentation. It allows Webb to dissect starlight with astonishing clarity, revealing the nuanced symphony of molecules, elements, and chemical interactions in atmospheres hundreds of trillions of kilometers away. In essence, the James Webb Space Telescope is more than a telescope. It is a time machine. Observing K218b is like peering 120 years into the past, capturing light that left the planet long before many of us were born. Even as the universe stretches that light through cosmic expansion, Webb can detect it, decoding the photons that carry the story of an alien world bathed in the gentle glow of its quiet red star. Through this patient, meticulous observation, humanity has gained its first glimpse of a living world far beyond our own, a world alive with subtle processes, a world whose molecules carry the story of ongoing biology. James Webb's greatest achievement is not merely in seeing the faint light that traveled across 120 light-years. It is in interpreting that light, in reading the coded whispers within it, and in translating photons into knowledge about life on another world. The key to hearing the whisper of life on K218b is a method called transit spectroscopy. As the planet drifts across the face of its star, a tiny fraction of the starlight filters through the planet's atmosphere. Each molecule in that atmosphere absorbs light at specific wavelengths, leaving behind a distinct pattern, a chemical fingerprint as unique as a snowflake, a human fingerprint, or the signature of an unseen hand upon a distant canvas. Among billions of photons, thousands of wavelengths, and the immense background of cosmic noise, Webb was able to detect the faint signature of a single molecule, dimethyl sulfide. Imagine trying to see the flicker of a firefly against the glare of a lighthouse, and then imagine doing this across the incomprehensible distances of 120 light-years. This is the subtlety, the precision, and the audacious power of Webb's observations. Months of observation, combined with advanced algorithms, artificial intelligence-assisted analysis, and the tireless effort of dozens of scientists around the world, made this discovery possible. It is not only a triumph of engineering, but a monument to human curiosity, patience, and collective intelligence, a testament to the human drive to reach beyond the known, to listen to the faintest signals of the universe, and to interpret them with rigor and imagination. At the heart of this discovery are two words: dimethyl sulfide. Though it may sound like an ordinary chemical, this molecule carries profound significance. On Earth, dimethyl sulfide is produced almost entirely by living organisms, from phytoplankton in the oceans to certain bacteria and algae. It emerges from the deepest layers of biological activity, a byproduct of complex metabolic cycles, carrying an unmistakable signature of life. No volcanic eruption, no tectonic upheaval, no purely chemical reaction is capable of generating dimethyl sulfide in significant quantities. Its origin is almost exclusively biological. This is why dimethyl sulfide is considered one of the most powerful biosignatures that we can detect on another world. Oxygen and methane can hint at life, but they can also arise from non-biological processes. Dimethyl sulfide, by contrast, almost uniquely points to active biology, signaling ongoing life rather than a fossil remnant of some ancient, extinct biosphere. Detecting this molecule on K218b brings humanity closer than ever to direct evidence of life beyond Earth. It is not merely the measurement of a molecule. It is, in a sense, the first time we have truly heard a cosmic whisper of life from another world. That whisper, carried across the void, suggests that somewhere, 120 light-years away, biology is at work, quietly reshaping a planet and leaving traces for distant observers to find. This discovery is revolutionary because dimethyl sulfide is more than a molecule. It is a chemical fingerprint, a biosignature, a subtle message from a living system that life can shape planets on a global scale. To appreciate its significance, one must pause, reflect, and consider the extraordinary power of life to transform an entire world, to engineer, to persist, and to endure across eons. Life is not a passive guest. It is a planetary architect, an invisible sculptor, shaping worlds over eons. It transforms the atmosphere, it redefines the chemistry of oceans, and it influences the physical surface itself, often in ways that are subtle yet profound. On Earth, over billions of years, life has fundamentally changed the planet, creating oxygen-rich air, altering ocean chemistry, sequestering carbon, and sculpting the very land beneath our feet. Mountains, soils, clouds, and currents are all, in part, products of life's patient work. If extraterrestrial astronomers were observing Earth from afar, they would not need telescopes that could resolve individual trees or humans. They could detect the imbalance of chemicals in our atmosphere and oceans and infer the presence of life long before ever seeing a single organism. This is the essence of biosignature research, to recognize the indelible chemical marks that life leaves behind, the subtle imprints of a planetary-scale force at work. Dimethyl sulfide, in particular, is remarkable because of its structure. Sulfur atoms bonded to carbon-based methyl groups, a molecular architecture that is elegant, intricate, and precise. These bonds are not trivial. They require highly specific enzymes, controlled energy flows, and metabolic pathways to form pathways that are themselves the product of billions of years of evolutionary experimentation. No geological, volcanic, or purely chemical process can produce significant amounts of this molecule without life. Its detection on K218b strongly suggests that organisms there are carrying out complex biochemistry, an entire planetary system of living chemistry. This is not a mere trace, a whisper of life struggling to exist. It is a chorus, a robust and ongoing signal that life is active, widespread, and reshaping its environment on a planetary scale. The implications are staggering. The concentration of dimethyl sulfide detected by Webb is higher than what we might expect from a planet where life is only beginning to emerge. It points instead to mature biological activity, possibly oceans teeming with organisms, atmospheric chemistry dynamically maintained, and interactions between the biosphere and the planet's surface occurring on a global scale. Life on K218b may not be fragile or transient. It may be a dominant, defining force, as integral to the planet as wind, water, and gravity, quietly yet persistently transforming the environment in ways we are only beginning to imagine. This discovery also invites profound speculation about the universality of life. If organisms on K218b produce dimethyl sulfide, it is likely that their biochemistry shares fundamental principles with life on Earth. Carbon, hydrogen, oxygen, nitrogen, and sulfur, these building blocks may be universal, forming the scaffolding of life wherever chemistry and energy permit. In other words, life may not be an isolated curiosity, a rare accident of chemistry on Earth alone. It may be common, arising wherever conditions allow, and following chemical patterns that are remarkably similar across vast distances of space. Yet, caution is always necessary. Science speaks in probabilities and evidence, not certainties. While Webb's data is compelling, it does not yet constitute irrefutable proof. Nature is capable of surprises, and complex chemical processes can occasionally mimic life in ways that challenge our understanding. Still, the statistical significance of this detection, the extremely low likelihood of it being a false positive, forces even the most skeptical scientists to reckon with the possibility it is among the strongest pieces of evidence humanity has ever observed, a potential answer to the question that has haunted us for millennia. Are we alone? The detection of dimethyl sulfide is far more than a scientific milestone. It is the first tangible whisper from a living world beyond our own, a faint chemical message carried across space and time. And as we listen, patiently and attentively, we realize that our long-standing solitude may finally be coming to an end. From 120 light-years away, beneath a hydrogen-rich sky, life may be breathing, growing, and subtly reshaping the chemistry of an alien world. The faint molecular imprint of this distant biosphere drifts across space, a soft and delicate whisper, reaching us as a reminder that life is not confined to the Earth we know. This discovery reshapes humanity's relationship with the universe. We no longer simply ask, could there be someone out there? Our questions become richer, deeper, more intimate. What is life like there? How has it evolved? Which principles does it share with us? It moves us from fear of the unknown to curiosity, wonder, and a sense of connectedness with the cosmos itself. The chemical signature in K218b's atmosphere is more than a reflection of a distant planet. It is also a mirror for ourselves, a reminder that the universe may be far more vibrant, more complex, and less lonely than we have ever imagined. Perhaps the silence we perceive in space is not empty at all. Perhaps it is filled with the faint, patient whispers of life. We are only now beginning to hear them. The detection of dimethyl sulfide on K218b is not just an astronomical observation. It is a moment of human awakening. For centuries, we have asked, are we alone? Until now, the answer remained speculative, built on theory, imagination, and limited observation. K218b may provide the first concrete clue that life is not unique to our world. It hints at a universe abundant with living planets, each with its own chemistry, its own ecosystems, and its own story to tell. This realization forces us to reconsider our place in the cosmos. Earth is no longer the solitary cradle of life. It is part of a vast, interconnected community of worlds, where life may arise wherever conditions permit. Through the extraordinary engineering, patience, and precision of the James Webb Space Telescope, humanity can now witness not only distant planets, but the processes shaping life there: oceans, atmospheres, and chemical cycles that speak to the resilience, persistence, and creativity of life itself. Life is never passive. It actively participates in the cosmos, leaving traces that ripple across space and time, reshaping environments and altering chemistry on a planetary scale. On K218b, dimethyl sulfide may indicate that life is widespread, influential, and transformative. A planetary-scale architect, sculpting its world as surely as wind carves mountains or water shapes valleys. Even more remarkable is the potential universality of life's chemical principles. If organisms on K218b rely on carbon, hydrogen, oxygen, nitrogen, and sulfur, similar to the life we know on Earth, it suggests that evolution may converge on common biochemical strategies wherever life arises in the cosmos. Perhaps the same molecular toolkit that allowed life to flourish on our planet is at work across distant worlds, building complexity, adapting to environments, and sustaining ecosystems informs both familiar and strange. This insight reshapes the search for life entirely. We no longer need to focus solely on planets that mirror Earth's size, composition, or atmosphere. Life may flourish under radically different chemistries, beneath hydrogen-rich skies, on worlds far larger than our home, orbiting stars far dimmer and cooler than the Sun, yet just as capable of nurturing complex biological systems. It may emerge in forms and scales that challenge our imagination, yet operate according to principles we can begin to recognize. In this light, the universe appears far more alive, dynamic, and abundant than we ever imagined. Every red dwarf star, once considered unremarkable, may host thriving biospheres, quietly rewriting the rules of chemistry, evolution, and planetary dynamics. Countless worlds may pulse with subtle activity, their atmospheres humming with chemical stories, waiting for patient observers to detect their faint signals. The detection of K218b's chemical fingerprint is more than a scientific achievement. It is a testament to human ingenuity, a reminder of the scale of possibility, and a profound illustration of what careful observation, rigorous analysis, and persistent curiosity can achieve. The whisper of dimethyl sulfide, traveling across 120 light-years, is not just a molecule, it is a message from the cosmos. It invites us to listen more closely, to embrace uncertainty, and to marvel at the richness of life beyond our home planet. In the end, K218b teaches us that life is not rare, fragile, or confined to familiar forms. It is persistent, adaptive, and capable of leaving its mark on worlds we have yet to imagine. It transforms, shapes, and engineers its environment, proving that biology is not merely a passenger in the cosmos, it is a force, an active participant in planetary evolution. And perhaps most importantly, it reminds us that the universe is not silent. The cosmic dark, once thought empty and unyielding, may be alive with gentle whispers of countless lives, their signatures written in the chemistry of atmospheres and oceans. Humanity is only beginning to hear them, only beginning to perceive the faint but persistent hum of life across the galaxy. And now, a new chapter begins. Astronomers are no longer searching solely for chemical biosignatures. They are expanding their gaze to technosignatures, traces of intelligent activity left behind by civilizations that may span the stars. Industrial activities, artificial pollutants, and unique chemical imbalances could reveal the presence of advanced civilizations even across interstellar distances. Detecting these synthetic gases impossible to form naturally would provide humanity with the first direct evidence that we are not only not alone, but that others have pursued technology, creativity, and curiosity just as we have. The universe may not simply be alive. It may be alive with civilizations, each leaving its own faint imprint on the cosmos. This pursuit now transcends biology, touching the domains of sociology, civilization, and the very essence of intelligence itself. Our search for life will not depend solely on the James Webb Space Telescope. Instead, it will be a coordinated, multi-layered effort, blending the capabilities of instruments on Earth with those in space, spanning radio, optical, and infrared wavelengths. Radio telescopes will listen carefully for artificial signals from star systems where Webb has already detected biosignatures. Optical telescopes will scan the dark sides of potentially habitable planets, searching for the faint glow of artificial illumination, city lights, or other evidence of technological activity. By combining observations across multiple wavelengths, scientists are attempting the most comprehensive search for life and intelligence ever conceived. A search that may transform our understanding of the galaxy itself. Future observations will become even more powerful with ongoing technological advances. Next-generation coronagraphs will allow Webb and other instruments to examine smaller, Earth-sized planets. Advanced spectrographs will provide unprecedented resolution for studying the subtle fingerprints of atmospheric chemistry. Enhanced data processing, including artificial intelligence, will extract faint signals previously hidden within massive data sets, revealing biosignatures that remain invisible today. This program is far more than a conventional scientific project. It is humanity's first systematic attempt to map life across the galaxy. In the coming decade, hundreds of living worlds, each with its own unique biosignatures, climates, and evolutionary histories, may be discovered. The universe may prove not only habitable but brimming with life, quietly thriving in corners we cannot yet perceive. At its heart, this initiative addresses one of the oldest questions in science: are we alone? The answer, it seems, may be a resounding no. We are on the verge of discovering the true extent of our cosmic neighborhood, the vast and living network of worlds that surrounds us. This transformative moment may not arrive with fanfare, dramatic announcements, or sensational headlines. It could unfold quietly, in a laboratory, as a scientist stares at a stream of data from the James Webb Space Telescope. In that instant, humanity's thousands of years of perceived isolation may end silently, but irreversibly. The evidence, when it becomes incontrovertible, will be undeniable. The convergence of specific atmospheric signatures will point unmistakably to life processes capable of transforming a planet's chemistry on a global scale. This is not mere speculation. It will be proof that life is a planetary force, a persistent and creative agent across the universe. Everything we thought we knew about our place in the cosmos will shift. Our assumptions about rarity, uniqueness, and isolation will be replaced by a profound recognition that life is abundant, resilient, and perhaps even inevitable under the right conditions. The discovery of K218b has already brought us to this threshold. With 99.7% confidence, roughly a 7 sigma statistical level chemical signs of biological activity have been detected 120 light-years away. The complex interplay of dimethyl sulfide, methane, and hydrogen in the planet's atmosphere reveals a chemical disequilibrium maintained only by active, living processes. This is not simply life existing. This is life flourishing, taking root and shaping a world on a planetary scale. Absolute certainty will come only when multiple, independent observations confirm these findings. Different telescopes will detect the same biosignatures. Alternative explanations will be systematically ruled out. Statistical confidence will climb from 99% to 99.99%, surpassing all reasonable doubt. When that moment arrives, its impact will ripple across every domain of human civilization. Science will undergo a revolution, as the realization that biology is not earthbound transforms our understanding of life itself. Philosophy, ethics, and religion will be challenged to reimagine humanity's place in a universe teeming with other forms of life. Technology will accelerate, seeking to explore, communicate, and understand these distant worlds. The psychological impact will be profound. Knowing we are not alone will dissolve the sense of cosmic isolation that humanity has carried since our first gaze at the stars. We will no longer view ourselves as a solitary exception. Instead, we will recognize ourselves as members of a galactic community, planets, ecosystems, and biospheres, each following its own evolutionary path, yet connected by the universal experience of life. This will not simply be new information. It will be a profound transformation of identity. The universe will no longer appear as a cold, indifferent void, a silent backdrop to our fleeting existence. Instead, we will begin to perceive it as a living, breathing, cosmic ecosystem, vast yet intimate, intricate yet harmonious, of which we are an integral part. Our deepest fear, the cosmic loneliness that has haunted human imagination for millennia, will be replaced by one of our greatest hopes, the realization of a universe teeming with life, quietly persistent across countless worlds. Yet this awareness brings with it responsibility, immense and humbling. As we begin to detect living worlds, one by one, we will confront ethical obligations toward them, toward their ecosystems, and toward the galaxy itself. This story will no longer be only about what we discover. It will be about how we respond, how we act, and how we cultivate respect for life beyond our home. It will challenge the very foundations of our ethics, philosophy, and imagination. The discovery of life on another world will do more than expand our knowledge. It will redefine humanity's relationship with the cosmos. It will force us to rethink our responsibilities as a species, venturing into space, not as conquerors, explorers without consequence, or collectors of curiosities, but as stewards of a universe in which life is rare, precious, and interconnected. The universe can no longer be seen as empty territory to be claimed, conquered, or exploited. Instead, it must be understood as a living whole, a vast network of fragile, interconnected ecosystems, each unique, each deserving of observation, care, and protection. Concepts once reserved for science fiction like the prime directive, the idea of non-interference with developing life, will become real ethical frameworks for debate and action. Do we have the right to alter or exploit biospheres on alien worlds? What responsibilities do we bear to shield them from harm, especially the harm that may arise simply from our presence, our curiosity, or our technology? These questions will guide the moral compass of generations to come, shaping the way humanity interacts with the stars. The moment we realize we are not alone will mark the dawn of an entirely new chapter in human history. We will move from a species that wondered if life existed elsewhere to a civilization that knows, with certainty, that it does. This knowledge will ripple through every dimension of human culture. Science will be transformed, philosophy reshaped, art infused with new inspiration, and spirituality confronted with a cosmos that is alive and participatory. Every child born after this moment will grow up with the profound awareness that life is not confined to Earth. They will understand themselves as members of a cosmic community, intimately linked to distant worlds by the shared experience of existence. This awareness will permeate education, ethics, literature, and the narratives we construct about who we are, why we are here, and what it means to live in a universe alive with possibility. The James Webb Space Telescope's detection of biosignatures on K218b represents the first and perhaps most critical step on this journey. It allowed humanity to hear the first whispers of life beyond the solar system, bridging the vast chasm between isolation and galactic citizenship. The chemical traces discovered in the atmosphere of a world 120 light-years away will be remembered as the first evidence that humanity's perceived solitude in the universe has ended, quietly but irrevocably. These discoveries reveal that life in the universe is not a rare accident, it is a recurring phenomenon. Where conditions permit, life emerges. Where life emerges, it transforms worlds, reshaping atmospheres, oceans, and even landscapes. The chemical signatures detected by Webb provide not only proof that life exists on distant planets, but also the broader insight that the universe itself is, at its foundation, alive, dynamic, and self-organizing. The James Webb Space Telescope has given humanity its first glimpse of our cosmic neighborhood. It has revealed a universe in which life may be the rule rather than the exception. We are no longer alone, and perhaps, in truth, we never were. The cosmos has always been alive, quietly waiting for humanity to develop the tools, curiosity, and understanding necessary to perceive it. Now, standing at the threshold of this extraordinary revelation, we witness a universe that breathes with the rhythm of countless biospheres. Each world carries its own chemistry, its own climate, its own story, a story unfolding quietly across the cosmic stage, imperceptible, without instruments capable of listening to its subtle language. The possibilities stretch far beyond anything we have imagined. A tapestry of life, woven into the very fabric of space. The universe is alive, and we are inseparable from its story. We are no longer mere observers, distant and passive. We are participants in a living, breathing cosmic ecosystem, bound by shared principles of chemistry, biology, and the inevitability of life. Here, at this threshold, we pause. We reflect on the immensity of what has been revealed, and we look forward toward a future where humanity embraces its role not as conqueror, but as guardian, explorer, and student of life itself, where curiosity is tempered by ethics, discovery is paired with responsibility, and the wonder of the cosmos is met with humility and care. The first whispers have been heard. They echo across 120 light years, carried by molecules, atmospheres, and light itself. And now, the cosmos waits for humanity to listen attentively, to understand deeply, and to respond wisely. For the story of life is not ours alone. It is the story of the universe, unfolding across stars, planets, oceans, and the silent, persistent rhythm of countless worlds.